numerous formulas on your formula sheet, correct? Many, many formulas. All the rest on that right-hand side that we have not talked about are in chapter 6. Welcome. So, sine squared plus cos squared equals 1 comes from the unit circle formula. Remember the unit circle formula I taught you? We do x minus h plus y minus k equals r squared. And h and k for the unit circle are 0, 0, so they go away. And then your r is 1, so it becomes 1 squared. And we end up with x squared plus y squared equals 1. This is from chapter 4. We agree? Okay. X and y on the unit circle are just sine and cos, yes? So I could go cos squared x plus sine squared x equals 1. Don't know why I changed my 2's. It's genetic because my daughter is, I looked at hers, I was like, you don't know how to keep 2 either. We both change our 2's the whole time. It's very weird. Yeah, no idea. Just how I feel for the moment. She does it too. Genetics. All right, the genetics of the 2's. And the conundrum of not knowing which one to pick. Okay, so if you look here, when you add 2 things, you can change the order. Correct? So we have sine squared plus cos squared x equals 1. The catch with every single formula in the world is you can rearrange them. So yes, sine squared plus cos squared x equals 1, but sine squared x also equals what? 1 minus cos squared x. This is true. And cos squared x also equals 1 minus sine squared x. Right? It's just rearranging formulas. The next 2 formulas come from taking that formula that we have above and replacing it, the sines and coses, with secants and all that stuff. And then getting common denominators, and you can get yourself a tan. Or replacing the sine with cosecant, and then getting common denominators you can replace with a cotan. So these come from that formula as well. But once again, they're on your formula sheet. They're called the Pythagorean theorem identities because they come from the Pythagorean theorem. And these 2 bottom ones come from this top one. They're right here. Okay? They can only replace squares though. So like if I had a sine theta, I can't replace sine theta with 1 minus cos theta. I can't do that. Okay? You can only replace squares. So it has to be a sine squared to get 1 minus cos squared. Okay? The squares can only be replaced with squares. The singles can be replaced with squares though. So for example, on your formula sheet, paying attention, you have cos theta equals 1 over secant theta. Correct? The singles can replace squareds, but the squareds can't replace singles. So that cos squared has to be replaced with a cos squared. This, I could say cos squared theta equals what? 1 over secant squared theta. Why would that be? Well, cos squared theta is just cos theta times cos theta, correct? Is that true? And then this cos theta, well, right, equals here, could be 1 over secant theta. And this could be 1 over secant theta. And that's the same as 1 over secant squared theta. So, if you can wrap your head around this, the singles can replace squareds. So, like, cos squared is the same as 1 over secant squared. But the squareds can't replace singles. So I can only replace this cos squared from this formula in for a cos squared. I can't go cos x equals 1 minus sine x, which people try and do. Can't do that. But the singles can go in as a squared. Because technically the singles you could just write out twice. All right, let's rearrange this one. If I want tan squared by itself, tan squared x equals secant squared x minus 1. We agree? And then the other formula you could use is 1 equals secant squared x minus tan squared x. And then same thing with this. I can go cotan squared x equals cosecant squared x minus 1. And then 1 equals cosecant squared x minus cosine squared x. Okay. What I have to say to you is, yes, those formulas are on the formula sheet. That's cool. The people who do really, if this unit is one that's done really well or terrible. Remember I told you that with like transformations, it's either done really well or terrible. There's no in between. Same with this one. Transformations, the reason why it's done really well or terrible is you know your transformations backwards and forwards. You flip when you need to flip. You don't go, do I keep it? Do I flip it? Do I remember how I said that? That would be wrong. The people who do really well in this unit are the people who know what formulas are on that formula sheet. So some people are like, well, I can just go searching. Just go searching means you have to actually search and hope to find. If you know what formulas are on that formula sheet, you know what you can replace. You know sine squared x plus cos squared x, whenever you see it, can be replaced with a number 1. Like if I ever see a sine squared x and a cos squared x, I can just cross it off and make it a 1, because sine squared x plus cos squared x equals 1. It's replaceable. Yes? The people who know what formulas are on their formula sheet do really well on this unit. And the people who search and find on their formula sheet and say, is that on there? And then, look, bad. Like really bad. So yes, you don't have to have your formula sheet memorized, but you kind of almost need to know what's on it, so you kind of almost need to have it memorized. It's the true fun facts of it. So those are the Pythagorean theorem ones, and then there's the double angle ones. The double angle fall between the sum below the sum and difference. So these are the sum and difference if you do another lesson on. So they're down here. Okay? What they mean is, if I had like the angle 30 degrees, I would find sine of 60. Because it would be 2 times 30 degrees. So you'd be technically finding sine of 60. That's the double angle identity. Now, the catch with the double angle is sine has one replacement. So if I have a sine 2x or a sine 2 theta, I can replace it with 2 sine x cos x. That's it. That's all I have. Then tan, same thing. Tan 2x is replaced with this ugly little formula. Okay? It's a fraction. You could end up with fractions and fractions. Cos 2x is the harder one because you have 3 options. Okay? It's just replacing other numbers, like I just replace like the cos squared x with 1 minus sine squared x, and I can get this. And just when I replace the cos squared x with 1 minus cos squared x, and I can get that. It's just using the Pythagorean identities in this original one to rearrange it and get the different other 2. So there are technically 3 you can choose from. So 3 gives us more options, which is great, but now I have options, which is not great. I actually have to figure out which one to do. So sometimes you look at the rest of the equation to figure out which one would be better to use. Okay? So, to solve some trig equations, you need to make substitutions using the trigonometric identities off your formula sheet. So, we have solved double angle ones before. Remember that every solving equation question can be verified graphically using your calculator. So, we will check with our calculator in the end. Okay. The catch with these is we've only factored in 30-1 so far. In 20-1, you guys have done these, but in 30-1, we have only factored so far linear ones or squares, like cos squared x equals 1, and you have to take the square root of it. Here, we're going to get trinomials. In order to factor a trinomial, you have to have all the same things. So you have to have all coses, or you have to have all sines. And then you can just do a normal trinomial factor by decomp or product sum. So here we have solve each equation algebraically over the domain 0 to 2 pi. Okay? I'm going to move it all to one side. So I'm going to have 1 minus cos squared x minus 3 sine x plus 2 equals 0. I have a problem. I can put the 1 and the 2 together, which can happen. There's also a catch where we can use a formula to replace this. The key thing here is, everyone listening, when I have a squared and a single and I need to make them all be the same, like all be coses or all be sines, the one to replace is always the squared one. Because if I replace the single one, sine x, the only thing I can replace it is 1 over cosecant. Does that make it any better? That makes it really awful. So I can't replace this one. So the only one I can replace is this. I can use the Pythagorean theorem identities to replace it. I could just replace the cos squared with 1 minus sine squared. Or, when I rearrange my formulas on the other side, is there a formula that is this? Perhaps. What does 1 minus cos squared equal? Sine squared. So can I replace 1 minus cos squared, take it off the paper, throw it away, and replace it with sine squared x? Because they mean the same thing. 1 minus cos squared x equals sine squared x. So I can replace this with sine squared x. Minus 3 sine x plus 2 equals 0. Okay, I always choose to factor it without the signs included. So I make myself have a let statement off to the side, and I go let m equals sine x. You need to have a let statement off to the side. You can't just all of a sudden put an m in there and not tell them what the heck the m is. They'll be like, where did this m come from? And you're like, they can figure it out their math. No, you have to do a let statement. So now I'm going to let m equal every sine x. So what does this become, this sine squared x? M squared minus 3m plus 2 equals 0. You see that? Then I can do what? Starts with an F. Factor. Product sum because I have a 1 in front. So I go what times what equals 2. What plus what equals negative 3. What's it going to be? Negative 2 and negative 1. So I'm going to get, I can go right to brackets only because there's a 1 in front. And get m minus 2, m minus 1 equals 0. M minus 2 equals 0. Remember, you have to show that step in the middle where you set them each equal to 0. And then m equals 2 and m equals 1. And then you have to stop yourself from boxing those. Because in 20-1, you would have been done there. M equals 2 and m equals 1. If you box them, was there even an m in the question? No, I put the m in there. Right? So I can't box these. What do I have to do now? Put the sine x back in. So I get sine x equals 2 and sine x equals 1, which we have solved these in chapter 4. We've totally solved these. I now just have 2 things to solve. And I need to find them between 0 and 2 pi. Do you see this? So I have to give it in radians. Okay, trick question for sine x and cos x. What do they max out at, the graph? 1. So the sine x graph would look like this. Technically, right? And this is 1, and this is negative 1. Whenever we solve these, whenever we solve any type of equation, we could actually put, this into y1 of our calculator, and we can put this into y2 and find out where they intersect. Whenever you're given an equation with one variable, you could always do y1, y2, find out where they intersect, x equals. You can check your x's always. Okay? So I'm going to draw the y2 as if I had my calculator here, right? So then y equals 2 would be up here. Wow, there's so many spots between 0 and 2 pi where this graph crosses. How many times does it cross? Trick question. Blue graph down here, black graph up here. How many times does it cross? It don't, right? So with sine and cos theta, or sine and cos x, if ever it equals anything greater than 1 or less than negative 1, we're going to get no solution because there's going to be no places where they cross. Because this graph only exists between negative 1 and 1. That's only sine and cos. Cosecant, secant, cotan, tan can be higher and can be lower. Because their graphs actually go higher and lower. Okay? Now let's look at where does sine x equal 1? Well, if I went back to the graphing part of it, oops, I made that bigger. If I went to the graphing part, let's go over here. I really only need this portion, correct? Because I need from 0 to 2 pi, my restricted domain. And this is 1. So this is y equals 1 in my y2, my calculator. This is y2 equals sine x. say? Y1, whatever. Where is it crossing at? Where is it intersecting at? 90 is a lovely answer, except we're in radians. So it's pi over 2. So x equals pi over 2. So I want everyone to put this into your y1 and this into your y2. Go. Make sure in what mode this time. You can be in degree, that's fine. Just make sure that you convert it to radians as an answer, right? So make sure you're in degree mode. But if we're in degree mode, what is our x min? What's our domain? 0 and 2 pi. If you're in degree mode, what's your x min? 0. And what's your x max? Oh. If you're 0 to 2 pi in radians, what would that be in degrees? 0 to 360. So you change your window to be x min from 0, x max to 360. You want to restrict it. And then second trace 5, enter, enter, enter. You want to find out where they intersect. Y1, Y2. You should all be getting 90 on your screen. So your Y1 can be sine x, your Y2 can be 1. You could go zoom trig to get it in degree mode and then change your window from 0 to 360. Why do we want to change our window from 0 to 360? So we don't give answers outside the domain. Yes? However, your answer is 90 degrees. I won't accept degrees, so you have to convert it to pi over 2. Right? You can do it in radians from 0 to 2 pi. The catch is it's going to be in decimals, right? And I don't know pi over 2 specifically perfectly in a decimal. So it's not as easy for me to see that. But you can. You guys try B. Go. So, I know right now I have cosines and sines mixed up, correct? Like mixed together. The one I always have to replace is the what? The single or the squared? The squared. Because the single I can only replace with 1 over secant, and that is not helpful, right? It makes you further away. I do know 1 minus sine squared is the same as what? What is 1? It is cos squared x. And then I have to move everything to one side because it's a quadratic. And I get that I learned in 20-1. Cos squared x minus 2 plus 2 cos x minus 3 equals 0. You can't just put m's in because you feel like it. You have to go let m equal cos x. So we get m squared plus 2m minus 3 equals 0. What multiplies to give me negative 3 and adds to give me 2? 3 and negative 1. Because there's a 1 in front, I can go right to brackets. M plus 3, m minus 1 equals 0. Do you think they'll have the option to you doing them backwards? Yes. Like you going m minus 3, m plus 1, they'll have the answer to that. You're making a new C. Then we have to set them each equal to 0. Remember I told you you would lose marks? M minus 1 equals 0, you still will. M equals negative 3, m equals 1. There was no m in the question, m is cos. So cos x equals negative 3. My cos graph goes like, starts at 0 and 1, and it goes down to negative 1, up to 1, down to negative 1, up to 1, correct? And then I have a horizontal line at negative 3 below. So how many times does that cross? It doesn't. So what would my answer be to this one? No solution, because there actually is no solution that I can find. Remember, extraneous meant I got a solution, she don't work. Correct? Extraneous, no solution, very different. No solution means I literally can't get one. I have a sine x graph, starts at 0, 1, goes down to negative 1, up to negative 1, up to 1, down to negative 1. I have a negative 3 line at the bottom. They literally can't cross. There is no solution that I can find, because the solution would be where they intersect, and they don't. Okay? Then this one would be where cos x equals 1. And where does cos x equal 1 on the unit circle? This is 1, 0, correct? Cos is x, sine is y, Calgary stampede. So, It's at 0 degrees. Now we have to ask ourselves, it's 0 degrees and 2 pi. 0 degrees? Come on, Lepp, government, get in the game. It's the radian. It's 0 and 2 pi. And then I move on. Before I move on, though, I should always check. Is 0 included? Is 2 pi included? Wait, oh my goodness. 2 pi is not included. What if I give 2 pi as an answer? You have to lose marks. You have to, because it is not an answer. Just like as if you giving 2 pi as an answer is equally as bad as giving pi over 3 as an answer. Neither of them are a solution. People are like, but it is no, it's not, because the domain does not have it in it. Okay? And be equally as bad as going x equals smiley face. It doesn't. And it doesn't equal that, and it doesn't equal 2 pi. So x equals 0 is my only solution. Okay? How they can give a big question like this in a numeric response. And it's just 0. All right. Oh my goodness. Now we have cos 2x's and a single cos. And we have sine 2x and it's... So, oh my goodness. Worst thing ever. When people go to the test and they're like, oh my goodness, Mrs. Lepp, you messed up. Oh, silly you. That's cos squared x. Put the 2 up, lady. No. Or you like don't even see it like that. You see it as a squared. And then you're like, sweet. Squared, single, number. I can just factor it. No. No. It's a cos 2x. It's a double angle identity. Now, the catch on the cos 2x's as opposed to the sine 2x's is there are 3 options, right? I have to replace the double angle identity because replacing the single, I only have 1 over secant. Doesn't help. There are 3 options that I can choose. The first one has a sine and a cos. It's cos squared x minus sine squared x. Now I have coses, sines, cos, and a number. So I'm still not better, correct? Then the bottom one has 1 minus 2 sine squared x. So then I would have a sine squared x, a cos, and a number. Is that helpful? No. I'm going to pick the middle one because the middle one only has what? Cos squared. And then I'd have squares. I'd have coses, cos, number. Right? And then I'd have all coses. We agree? So I'm going to choose the second one because, and why do I choose it? Because I don't just throw in a thing and guess. I actually look at my whatever I have left, and what else I have in that equation is all coses and just numbers, correct? So the best thing to replace this with would be the one that has only coses in it. Yes? And that one is 2 cos squared x minus 1. So I'm going to replace this with 2 cos squared x minus 1, and then this just stays plus 1 minus cos x equals 0. Do you see how you have to educationally choose which of the 3 to use? Now the 1 and the negative 1 cancel. And so I have 2 cos squared x, bless you, minus cos x equals 0. And then I get a whole bunch of people stuck because they're like, I can't do a trinomial factor. It's garbage. You need to give me a number. Like, you're not happy when those numbers cancel. So if we're stuck, replace with a letter, right? If we're stuck and we can't see that we could take a cos x out of both, go let m equal cos x. And we get 2m squared minus m equals 0. Whenever I don't have a number at the back, what could I just do? GCF. And to get a greatest common factor of m. So I'm left with 2m minus 1. Some people like just keeping the coses and they take a cos out. You can do that and not use a let statement. Then we have to set them both equal to 0. M equals 0. 2m minus 1 equals 0. This one is going to be 2m equals 1. M equals a half, bless you. And they split, but we didn't actually have m's, we had coses. So cos x equals 0. And cos x equals a half. Now, it's between 0 and 360, not inclusive of 360 degrees, right? So I go, where is cos x equals 0 when x equals 0, which is where and where? Nope. 90 and 270. It's where x equals 0, yeah. So my answer for this one is going to be x equals 90 degrees, comma 270 degrees. And then cos x equals a half, positive a half, so it's in quadrant 1 or 4, because that's where CAS rule tells me it is. Cos x equals a half at 60-degree reference angles. It's also when x equals a half, so it's here and here, which is 60 degrees and then they'll always put them together and usually in order. So x equals, I got a lot of people going cos x equals on the test. You're lucky I'm nice. Cos x doesn't equal this. X just equals this, right? I also got people who just gave me answers and boxed them. No x equals. You have to have x equals, okay? Because that's what you're telling it equals. If I took, watch this, if I took 90 degrees and I plugged it into this side of the equation, equals 0, I would get 0 equals 0. I can check every single answer. Remember, we checked answers since we're little. Put something into the left side, see if it equals the right side. Yes? I could put all 4 of these answers in for x, and they would get 0 equals 0. All 4 of them. And I would know I was right, because you can check your solutions whenever you solve. So we get x equals 60 degrees, 90 degrees, 270 degrees, 300 degrees. Terms that you can't fix. Okay, so sine 2x is 2 sine x cos x minus cos x equals 0. When solving, listening, when solving we never divide. We will divide off half of our term. Instead of dividing things, what's another way to divide out a term? What's another way that I divide out a term? Factoring by GCF. So if you want to take the cos x over and divide the cos x off, you got rid of half of your solution. So instead of dividing that cos x off, let's think of another way, an alternate way. So what's better is to actually, instead of division, which we're not allowed to do, GCFing actually divides it out. Remember when you take a GCF out, you're actually dividing that term out? Same thing. So we're actually going to take a cos x out of both terms, and we're left with 2 sine x minus 1. The reason why I left this is most of you will divide the cos x off because it gets rid of it, which is ish good, but it gets rid of all the answers where cos x equals 0, right? And we don't want that. So if you're stuck, could we not have replaced those with 2 different letters? I'm going to show you. I could have, if I got stuck here, I could go let m equal sine x, let n equal cos x, and instead of taking that out just the way it is, I could have went 2m n minus n equals 0 and took an n out. So I could have done that as well. If you don't like dealing with the coses and sines, you can replace it with m's and n. Okay? Here we're going to have cos x equals 0. Half of our solutions come from that. 2 sine x minus 1 equals 0. 2 sine x equals 1. And sine x equals a half. We're between 0 and 360 degrees, not inclusive of 360. Cos equals 0 here and here, which is 90 degrees and 270 degrees. And then we need where sine x equals a half. Sine is positive in quadrants 1 and 2, and 30 degree reference angles when sine equals a half. This is 30 and this is 150 degrees. Don't forget your degree symbols. There is a radian measure, whether you like it to be or not. And then we write them all together, usually in ascending order: 30, 90, 150 degrees. Okay, then we're going to flip over to example 3. Actually, I want go do example 4 first. And do example 4 from, we'll say, 0 to 360 degrees for now. Then we'll come back to 3. So I know it says general solution. I went ahead. I know this one says general solution. For right now, I just want you to do from 0 to 360. And we'll talk about general solution. So you're doing A and B. Sine 2x is the one I have to replace, correct? The singles I can't replace. I'm really trying to drill that into your heads because when quizzes come or tests come, you guys try and replace the singles. You can't do that. Well, you can with 1 over secant. Once again, not helpful. Okay? So sine 2x is not a mistake. It is sine 2x. It is a double angle identity. There is one formula I can replace it with, which is 2 sine x cos x. And then I need to move this over, minus root 2 cos x equals 0. What could I take out of both of these terms? What greatest common factor? Cos. So I'm left with cos x and then 2 sine x minus root 2, which actually makes me happy because I know that that is going to be on the unit circle as well. Sometimes they're not. So then I get cos x equals 0. I have to do this step. 2 sine x minus root 2 equals 0. 2 sine x equals root 2. Divide by 2. Sine x equals root 2 over 2. Okay? Where does cos x equal 0? We should have this embedded in our brain at this point because seemingly this has happened on all 3 of the last questions. So x equals 90 degrees and 270 degrees. Before I move on, that is the generic answer to 0 to 360. This is asking for a general solution. How could I write this as a general solution? X equals 90. I technically could do this. I could go 90 plus 360 degrees n, NEI. 270 plus 360 degrees n, NEI. I could write them both separate, and I would be correct. But if I wanted to put them together, what are they? How many degrees apart? 180. So I could go plus 180 degrees n, and then I have to follow behind with n as an element of the integers, not because I memorized it. Why is it integers? I hope someone knows and is just not answering me. Why is it integers? Yeah, you have to times it by like a 1 or a 2 or a -1 or a 0. You're not timesing it by 1.5. That wouldn't work. Or 80 times 0.5 would actually be adding 90. I don't want to add 90. Correct? So the reason why it's integers is because I need 1. I need to multiply by 1 or 2 or 3 or 4 to get it to do that coterminal. Right? Remember, if you don't know why something is, you ask why. Because you won't screw it up if you know why. Okay? This one is root 2 over 2, which is here and here, which is 45 and 135. I can't put those together, correct? Like this is 90 apart and then 270 apart. Like I can't put those together. So I have to do them separate. Does it make sense why we have to do them separate and why we can put them together? Because that why is the important part here. We don't know why. We just try to do something memorization. So it's 45 degrees plus 360 degrees n, NEI. And then x equals 135 degrees plus 360 degrees n, NEI. Make sense? So you would need this and these. Knowing that, I want you to finish B. We're going to go through it tomorrow in general solution. See if you can.